Hello everyone, my name is Anoop Cherian, and today I'm presenting our CVPR paper titled Are Deep Neural Networks Smarter Than Second Graders? This joint work with Kuan-Chuan, Peng and Suhas Lohit at MERL and Kevin Smith and George Tenenbaum at MIT. In the recent times, we have seen several applications of deep neural networks that need superior cognitive abilities to solve. So are we there yet in achieving artificial general intelligence? In this paper, we ask several key questions, such as how well do deep neural networks perform on tasks that need broad skills? How do they transfer knowledge to solve new problems? How fluid are they in acquiring new skills? And how effective are they in the use of language for algorithmic reasoning? How should we go about answering these questions? Where should we even start? Are state-of-the-art deep neural networks capable of emulating the thinking process of even young children? In this paper, we propose SMART, which stands for Simple Multimodal Algorithmic Reasoning Task. The task is to design deep neural networks that have foundational skills to effectively analyze, interpret, and solve simple algorithmic reasoning puzzles and generalize to new problems. We propose a SMART 101 dataset consisting of 101 distinct vision and language children's puzzles. Using SMART dataset, we show that the current large language models and visual reasoning pipelines do not generalize well to tasks that need broad skills. In order to construct the SMART 101 dataset, we took the puzzles in the dataset from the math competition, which is called Math Kangaroo USA Olympiad. It's an annual math competition for school kids from 1st to 12th grade. We selected puzzles from 2012 to 2021 competitions designed for children of 1st and 2nd grades, which is in the 6 to 8 age group, used only the simple puzzles from the MK competitions. This is an example puzzle from the competition. There is a question part of the competition, and then there is an image part. The question, for example, in this case, it asks, Sparrow Jack jumps on a fence from one post to another. Each jump takes 1 second. He makes 4 jumps ahead and then 1 jump back. Then he again makes 4 jumps ahead and 1 jump back, and so on. In how many seconds does Jack get from the start to finish? In order to answer this question, you need to interpret the image. And first task would be to find how many poles are there in the fence from the image, and then come up with an algorithm that will solve this task, and then select the answer from one of the 5 options given at the bottom. Now, we have 101 such puzzles in our dataset, but that's not sufficient to train deep neural networks. We need to have a large number of data points. In order to do that, we came up with this idea of programmatically augmenting the puzzles. So we create computer programs that can augment every puzzle in this dataset into new instances, as shown over here. So at the bottom, you can see several instances of the puzzle, which are produced by changing the arguments of the computer program. With this approach, we generated 2,000 instances for every one of the 101 puzzles in our dataset. This amounts to nearly 200K puzzles or puzzle instances in our dataset, and we categorize these puzzles into 8 different classes corresponding to the skill that is needed to solve the puzzle. For example, there are classes such as counting, path tracing, measurement, pattern finding, spatial reasoning, algebra, logic, and arithmetic. As you can see from the previous puzzle, it's just not one skill that is needed to solve that puzzle. For example, counting the number of poles on the fence, but you need other arithmetic skills as well. So there is a composition of skills that are needed to solve the various puzzles in our dataset, and that compositionality is shown in the figure B. This is an example from the spatial reasoning class, and the augmentations of the puzzle at the top. There's another instance from the arithmetic class. In order to evaluate state-of-the-art deep neural networks for solving the puzzles in our dataset, we came up with this meta-learning based reasoning baseline. The key idea of this baseline is that it can take any image backbone, state-of-the-art image backbone, and any state-of-the-art large language model question backbone, and there is a set of fusion layers that combine the output or the feature embeddings from the image and the language backbones to come up with an answer, which is selected by the puzzle head at the extreme right. Coming to the experiments, we have 4 different splits on our dataset. The puzzle split, which checks for extreme generalization, where 21 out of the 101 puzzles are not shown to the architecture during training, and so the system has to learn to generalize to unseen classes or unseen puzzles. Few shot generalization, where out of this 21, some of the instances from these 21 puzzles used during testing is shown during training. And the supervised learning setting, where all the puzzle instances are available during all the puzzles are available during training, but not all puzzle instances. So this is checking for the in-distribution generalization and answer generalization, where answer split, where some of the answers in the supervised training setting are hidden, and it is available only during test. In order to evaluate the performance of deep neural networks, we came up with two metrics. One is solution accuracy, and the other is option selection accuracy. The latter is evaluating the accuracy of selecting the correct answer or answer choice from the 5 options. As these puzzles are actually taken from the math competition, we have the performance statistics of the kids who participated in this, and we find that averaged over 3,000 kids who took the Olympiad in 2020 and 2021, and the puzzles that we used from this Olympiad for our data set, 77.1% is the accuracy of the children. Whereas the accuracy of deep neural networks is substantially lower, and it's close to random accuracy. And we also experimented with the performance in the supervised setting. We see that the performance, as expected, is higher than that of extreme generalization experiments, but it's substantially lower than that of the kids still. We evaluated various transformer models, as well as large language models, and even vision language models such as CLIP and PLAVA. And we find that in supervised setting, the performance is still in the ballpark of 43% or less, whereas a kid's performance in the generalization setting was 77%. We also evaluated the recent large language models such as ChatGPT or Bard, Peng, and GPT-4, etc. We find that ChatGPT seemed to perform the highest, which is 36.4% on a subset of our dataset, which consists of only the text part of the puzzle and not the image, because GPT models currently available are not multimodal, so they cannot look at the images. So to conclude, we asked the question, are deep neural networks smarter than second graders? Our analysis on our dataset shows that they are not yet. However, the recent large language models, such as ChatGPT, appear to showcase convincing out-of-domain generalization abilities. Nevertheless, there appears to be gaps in its reasoning and perhaps a more systematic adherence to the foundational skills of learning and reasoning might be important. Thank you so much. And the Smart 101 dataset is publicly available. Feel free to stop by at our poster for questions. Thank you.